Hello, my name is Trevor Brown, and today I'm doing a presentation for CIS 321 Emerging Information Technologies. It is the spring semester of 2018 at Western Kentucky University. As you can see up here at the top, here's my login name, and here's the link to the submission for this project, just so you know it is me. Today's topic, we're going to discuss software-defined networks and mesh networks and how they're going to completely um, evolve the traditional computer networking and environment. To give you some background we'll start with software-defined networking. Basically, a software-defined network is a network architecture that's essentially decentralized. However, there is an aspect of this network that is centralized, and that is our control module. And we'll discuss that here more in a moment when we take a look at the architecture diagram. This kind of architecture is very popular in cloud computing because it offers some essential aspects that cloud computing depends on, such as scalable networking. So being able to dynamically configure your network based on the workload that's received. Additionally, when if a large workload is received, it's going to effectively load balance its job request across multiple machines, multiple servers. And two, depending on what kind of networking you're trying to perform, whether somebody's connecting remotely to your machines directly or if they're using a web interface, you also want to perform some traffic segregation where certain traffic requests are handled over certain ports, over certain IP addresses, instead of just sending it all through one bottleneck. As we look here, here's a comparison between the traditional networking model and a software-defined networking model. As you can see on the left-hand side, we have traditional networking. We have 4 devices interconnected in such a way where they're not all connected directly, but there is a route between each device. There is at least one. There's multiple pathways you can take to get between devices. Each network device here, you can think of a network device as everything from a router or switch all the way down to a PC or some other networkable device. We have a control plane, which would be the actual interface of the device, Ethernet, Wi-Fi, things of that nature, and the data plane is the unit of data that's either user-generated or system-generated. As you can see here with the traditional networking model, the issue with this is if two of these nodes go out, depending on which nodes, it may be impossible to connect to the other nodes. So if you see here these 2 nodes over here, if they're trying to communicate with each other, they have to go through either this node or this node. If both of these nodes fail, they can't communicate they can't communicate between each other. But if one of these nodes go out, you still have a pathway that exists. So it's good. It's got some redundancy here of the connections, but it's not effective if both go out. With a software-defined network, this is completely abstracted, and there's no concern about whether or not a node's available. We have one central control plane. However, the rest of the nodes can be dynamically added and removed from the network, and they just depend on a controller agent, which takes the place of the control plane for each device. Once all interconnected, the devices have the ability to connect via an application programming interface, an API, to various applications. So essentially we have a model here that allows for a programmable network. As we see here, some of the benefits include that added functionality, which would be a programmable network, meaning you can write software that can directly interact and modify the network in any way possible. Traditionally, the way this would work is adding machines to an existing network, and then software within the router or the gateway of the network would assign an IP address and perform whatever other adjustments were necessary. Another thing is with software-defined network is there's swift recovery from failures. We saw in that model before the potential of failure if 2 nodes failed in that small network. The other 2 nodes can't communicate. But with a software-defined network, it's still possible for those nodes to connect and communicate with each other regardless of how many nodes are attached to the network. With that said, the software-defined network removes some of the other traditional networking issues. The configuration being directly in the gateway or the router of the network. Now it's spread across the network and can be retrieved and updated depending on what machines are attached. Another thing that's improved is latency. So latency is the amount of time it takes for nodes to communicate within a network. When you have a software-defined network, all nodes are aware of every other node. So the latency is drastically reduced instead of in a traditional network where the node has to call out to the gateway for it to report the nodes on the network, no longer an issue. So how are software-defined networks applied in today's society? Well, major cloud service providers, CSPs, Amazon, Google, Microsoft, they all incorporate software-defined networks in their deployments for people. This is mostly due because of the nature of virtualized environments. Because a software-defined network is essentially a virtual network, not a necessarily a virtual private network, a VPN, but it is a type of virtual network. Some other situations where software-defined networks have been applied today are private implementations. Microsoft offers with its Server 2016 product a way to do software-defined networking in your own data center. The same applies too with Red Hat, Enterprise Linux, and other various forms of Linux. And again, virtualized environments are already able to do this because of their inherent nature of being abstracted already. Moving on to the next type of network that actually I would consider a subset of software-defined networks are mesh networks. And these are networks that rely on data hopping between nodes to transmit data from a source to a destination node. So instead of having a central point of access, a router or a switch connecting all the nodes, what we have instead is the ability to transmit data in a fashion that is just using the devices on the network as a router or a switch, a, 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 a direction, a traffic cop, so to say, the way they transmit. Um, the way this works, the architecture of a mesh network, sort of follows a star ring network topology hybrid, I like to say. That being, the star aspect would be it's able to connect across the network. Instead of connecting to a central point, it connects to other nodes, and ring being that it's able to pass data around to its neighbor nodes. This kind of topology is very popular with IoT devices or Internet of Things devices, such as these smart lights, smart speakers, smart switches, anything that is essentially smart today can use a mesh network. So we see here the reason they're able to do this is usually because of either Wi-Fi or Bluetooth, and there's two other primary protocols that are being used today called Z-Wave and Zigbee. As you can see here, here are some specifications on those types of protocols. You can see they're sort of, compared to something like Wi-Fi, they're not as great. Sure, like Zigbee, for instance, can support more devices uh, depending on its configuration, but the data rate and frequency are the main things you want to look at here when comparing them to something like Wi-Fi. The closest thing to even a Wi-Fi in terms of frequency that we have is Zigbee with a max of 2.4 gigahertz. This is the frequency that Wi-Fi's versions 802.11 G and I believe B also used in their early stages, and I believe N could also use it, but now it's starting to shift to a 5 gigahertz range. And with Z-Wave, you can see the frequency is completely, just offset. It's just way lower than the Wi-Fi. But the benefit is with a software-defined network, and you'll see here in a moment where this will apply, a software-defined network could easily do some frequency matching, or if there's frequency mismatch, it can act as a bridge between the two types of protocols, and in turn join them together in such a way that they can be used concurrently. Again, some benefits of a mesh network: there's no need for multiple access points, as each node in the network acts as an access point to each other, and this could potentially remove a central gateway or router. Now, I do see this in a traditional network being a thing in the future, not necessarily anything soon becoming mainstream, but there is actually some products out there on the market that are already achieving this with Wi-Fi. Some other potential benefits would be replacing traditional Wi-Fi networks, which require broadcasting from a central point out to other devices. Instead, we use an interconnected network of nodes to achieve the same effect. And two, if you can't afford an existing router that can perform these functions, ASUS produces software for their routers, pardon me, that can achieve the same effect. So places where we see mesh in today's society, Zigbee and Z-Wave offer devices such as lights, switches for lights, door locks, so on and so forth. And when I say they actually just provide the protocol. They don't necessarily provide the equipment themselves. Google Wi-Fi is actually a native Wi-Fi mesh network that's readily available in the market. And we can also see this popping up in settings such as industrial settings for monitoring industrial controls, motor controls, and monitoring these devices as well. And we can also potentially see it with automobiles, since automobiles are composed of many sensors. Instead of having to go through and find a way to join them together, we can just rely on them to communicate with each other through a series of sensors and to effectively relay that data. And then while they're passing the data along, they can also collect it and use it as necessary. As we see here, this is potential for an automatic driving car. That may be the future for the automatic driving car, is having a mesh network integrated into the vehicle. So again, the way I see the future of software-defined networks and mesh networks coming up is they are being paired together in the home, where in such a way that all of these devices that we own that are networkable can actually communicate with each other without the need of a central access point or some kind of conversion, a physical conversion device such as a bridge to hop between something like a Wi-Fi network and a Zigbee Z-Wave network. Another thing too is with the programmability of a software-defined network, we could see a middleware that pops up, uh, probably varying per manufacturer of the devices, that allow the ability for devices to programmatically adjust network settings and modify devices over a network in such a way just because of the middleware's availability. Another thing that's coming up, another emerging technology that benefits from this, is basically this concept of a software-defined everything, which applies to the internet becoming software-defined, all local area networks becoming software-defined. Basically, all that means is instead of having a configuration that is set just for a specific device to control everything, or distributed devices controlling everything, everything controls everything in a way. Not in a conflicting manner, but in a way that's unified and seamless. Here are my references for this research that I've done. I will put these links in the description for your observation. I appreciate you taking the time to listen to this presentation. If you have any questions, comments, or concerns, feel free to comment them in the description or in the comments below. I'd be more than happy to hear your thoughts on this topic. Maybe help me expand my knowledge on the topic as well. I'm up to learn anything new. Thank you and have a great day.